So first I want to give you a little bit of history about who I am. So as Matt said, my name is George Wilson. I've been working on ZFS for about 10 years now. First initially with Sun Microsystems, and then went to a small startup called Delphix, where I'm still there today. I kind of started out with ZFS in kind of a weird way and got really, I started out more as a system administrator than a developer of ZFS, so I was actually working in a different engineering team before I decided that, hey, I really like what this is doing and the direction it was taking. And I had been used to using logical volume managers and partitions, and as soon as I saw this, I'm like, hey, I'm sold. So I want to find out more about the technology, and that's how I got involved with ZFS. Joined the development team after doing some initial projects for them. They asked me to come join them. Have loved it ever since. One of the things that is kind of a hobby of mine is I do pool recovery, which is a little sadistic. I don't know why. I think I started off primarily because I wanted to make sure that code that I was writing wasn't actually impacting, users that were deploying it. So that's where I started doing it. Kind of loved it, and still do that today. So I get contacted by various people to say, hey, can you help me try to recover this pool? Success rate is typically higher than you would expect, especially with some crazy things, and I'm happy to share war stories. We'll do that after the session. So that's a little bit about what I do. I'm happy to also say Delphix is, we're a great contributor of open source software. We are probably the largest contributor to OpenZFS. We've been building up our ZFS team. We're actually hiring. We just opened up a new Atlanta engineering office, so that's really cool, and that's where I'm based out of. So first I'll talk a little bit about OpenZFS, and how many people are familiar with OpenZFS? Great, okay. So OpenZFS is kind of interesting because it is run on multiple platforms. You can run it today on Linux. OS X just had a new deployment that works on El Capitan. Illumos, if you're kind of Solaris knowledgeable, and also FreeBSD. We also just announced our new GitHub repo. So OpenZFS was designed to allow all these different communities that are out there making changes to the ZFS code base and kind of organize and bring them all under one umbrella. And that's what OpenZFS does. So we now have a new repo that is based off the Illumos gate, and it allows people to actually do pull requests and bring in and get new enhancements into the main trunk of OpenZFS. And I posted it up there. It is community driven. We just finished up our annual developer conference in San Francisco, which was really well attended. If you are interested in any of the talks, they are available on YouTube. You can also find them from open-zfs.org or see me afterwards. So it's kind of interesting. I was here 2 years ago talking about OpenZFS. We had just announced the OpenZFS umbrella project. And one of the slides that I was looking back through an old deck, and I saw this slide, and it said, wow, here's the future of OpenZFS, and here are some features that we're going to be coming out with. So here I am 2 years later, and over 60% of the features that I mentioned 2 years ago are complete. The three you see here in blue were actually the features I talked about at that conference. The ones in red hadn't been dreamt up yet. Everything else is in the process of either has already been committed or is currently under review. So there's a lot of interesting things that have gone into the OpenZFS project. I'm not going to talk about them all here. I will talk about some interesting things that are that have recently integrated and are coming very soon. So, what are we going to talk about? As system administrators, most often you're contact and say, hey, I need you to deploy this new system, or I have some extra hardware. I mean, how many people work for a company where you have excess hardware and it's all leading edge stuff? That's what I thought. So that's one of the things and one of the challenges that people face today is we have a lot of hardware oftentimes, or we're moving to a virtualized world. We're often being asked to do more with less. And here are just some things that people think of when think about more with less. It's You want it to be more robust. You want it to be easy to recover if there's a problem. You want to be able to get it back up and running as quickly as possible. You want it to be more efficient. So depending on what resources you have, even if it's like an ancient box, I want it to be very efficient on how it uses those resources. And we want it to perform well. So everybody wants things to just go faster. So those are the things we're going to talk about today. How do we actually achieve that? So first I want to talk a little bit about some of the robust things that we've done to replication. How many people use ZFS send and receive? How many people love the fact that you have to restart it every time you have a failure? Okay. This is one of the biggest issues that we've seen with ZFS send and receive. So those that do like replication and actually send data from one system to another have probably run across this. And this was a legitimate problem that we encountered at Delphix and needed to solve. So we have customers that actually replicate data all over their data centers and even across the globe. In particular, we had one customer who does a replication. The replication is so big and going over such a small pipe that it takes 10 days to complete. Unfortunately, they had a network outage every 7 days. So they would get 70% of the way there, boom, things would have to start over. So big problem for us to go off and solve. And that's exactly what we did. So we're now introducing Resumable send and receive, and we came up with a very simplistic design for it. So the idea is we just simply keep on the receiving side, we just keep some state. We keep track of what was the last object that we saw, as well as the last offset in that send stream that we were processing. And then on the sender side, we just simply have to pass that information over and say, hey, start the send stream from this point instead of actually starting from the beginning. But we also wanted to make sure that this was unidirectional. So those that have played with send and receive know that it's one of the advantages we think is the fact that you don't have to kind of create this two-way handshake between the receiver and the sender. We can simply just say send, you can pipe it to SSH, mbuffer, netcat, and then receive it on the other side. We don't have to have like this fancy orchestration between the two different programs. So we wanted to keep that intact, and that's exactly what we did. We now have this receive token that you can now query as a file system property on the receiver side. And it's just this kind of opaque ASCII blob of text that encodes into it the object and offset information. I'll show you exactly what that looks like. And so once you get that, whether you get it programmatically, you get it by somebody like, emailing it to you, then you can just simply provide that to ZFS send and pick up from where you left off. So this is what it looks like now. So we have the send going. Receive now takes a new flag, which is the -s to save state. And this is going to keep and generate that token that I just mentioned as a file system property. If there's a failure, you simply run ZFS get, the property in this case, receive resume token, and then you can pass that token to the send command. And again, send it back over ZFS receive or SSH or mbuffer. Yes? There's one token for the send stream that you're currently receiving. So if you're sending an incremental, then there's a token associated with that. So, and it's going to be for that file system that's being received. So if you're sending like, tankfs, then tankfs on the receive side now has this token that's been added to it. I have another example where hopefully that'll clarify it. And what this token does is it actually tells us exactly where in the snapshot we were and where to resume. It also encodes into it these special features. This is something that's relatively new in that the send stream itself has information about features that are supported on the sending side, so the receiver has to have the comparable feature enabled. If for whatever reason you were doing a resumable send and you're like, I really don't want to resume it, you now have to use this -A to abort it, because what's happened is you've actually kept the blocks and allocations that you've done on the receiver side now stick around as part of saving the state. So if we look at this in more detail, this is just providing the verbose flag, but here's the token and what it looks like. In this case, this is printing out the information that that token just generated. So what's encoded in this token is this unique identifier, the object information, the offset, how many bytes we were into it, and the unique identifier of where we're sending it to, and then also information about the snapshot. And then it just simply picks up. If we actually dump this out, how many people have used ZStreamDump? Okay. If you do a lot of send and receive, and you ever want to inspect the stream, really cool tool. Built as part of the ZFS project, but it lets you inspect what the stream looks like. So what this is doing is it's sending it to this program and saying, dump this out. Don't actually receive the data, but show me what the contents are. So here we are. We're resuming from this particular object, 2134, this offset, and you can see the very first object we start to process is object 2134 and that offset. So any data that was sent prior to that, we simply just skipped over. So now you can resume right from where you left off. So if you have any kind of network outage, or even you're in the middle and all of a sudden somebody says, hey, this is impacting my performance, you can stop this, save that state, restart it after hours, and actually pick up where you left off. Add to that a way that you can actually avoid having to compress the data. So a lot of times we're sending data from one system to another, but we're having to send it over some very small pipe. So if you're having to send the data uncompressed, we're talking about taking a long time to ship those blocks over. So the problem is we want to reduce the bandwidth. So in this case, we're talking about a 35 gigabyte snapshot that we're trying to send. So A at snap is that 35 gig worth of data. And one way a lot of people solve this is they use Gzip. Anybody ever done this? Yeah, so this is a kind of a common practice of like, hey, we want to compress that stream down before we actually put it over the network. So we end up reducing the amount of bandwidth that we take on our network. And then we uncompress it on the other side. So this is what it looks like. We read the data from ZFS. It comes into Gzip as uncompressed. We compress it. We achieve our goal of sending less data. We decompress it on the other side, and then we just receive the stream. Everything works great. Or normally it works great. But the problem is when you look at this, we're actually spending a lot of time decompressing the data because presumably it's already compressed on disk if you have compression enabled on your data set. So you read it from disk, you uncompressed it, you just used some CPU cycles. You then compress it again with Gzip, so you use some more CPU cycles. And Gzip, of course, is not the most gracious about giving back CPU cycles, so it likes to take as much as possible. You then send the data, you get it to the other side. Again, we're using CPU cycles to uncompress the data. We receive the stream, and then we pass it to ZFS, which, again, is probably compressed, so we're compressing it back again. So we wanted to solve this problem. And the way we went about it was to simply, let's take out all the compress and decompress stages that normally appear in this typical workflow. And if we can do this, then we can have a very efficient way of sending data compressed and writing it compressed without having to use any additional CPU. And this is what it looks like. So we're introducing the DashC flag. The long option is -- compressed as a new flag to ZFS send. So in this case, that same 35 gig snapshot has compressed down to 13.2 gig. So we're taking advantage of whatever compression ratio I have on disk. I'm now achieving this as part of my send stream. So if I'm getting a 3x compression ratio, then I should be able to get a 3x reduction in network bandwidth when I do that send. We also aren't achieving any bottlenecks on our CPU when we're actually having to compress and uncompress the data. They simply fall out, and we'll see why in just a moment. And again, the compression ratio that you see is the network savings. So in our simple test here, what we accomplished was we had a file system that had a 2.67x compression ratio. So we took 35 gigabytes, we compressed it down to 13 gig. That's what we sent over the wire. We got a speed up of 2.5x, and we actually reduced the amount of sending CPU by 2.7x. This doesn't account for the amount of CPU we saved on the receiving side, because when we receive it, we're not having to recompress the data. We just simply got it compressed, and we're going to write it. Now, the thing to note here is that this does require one other feature that I'm about to talk about. And it does require a feature called compressed arc. Are people familiar with the term arc as far as ZFS is concerned? Great. So I just want to kind of highlight some things in the arc and kind of give you some details about like its internal workings so you can understand how compressed arc is implemented. So the first thing to note is there's these kind of three big data structures that we maintain as part of the read cache in ZFS. We have a big hash table, which uses this triple. It's a SPA GUID, some kind of virtual address, which is the virtual address of the block on disk, and the birth time of when that block was actually created. And we use that as a way to hash into a big hash table. What we hash in there are these things called arcbuff headers, which is, you can think of it as just a piece of metadata, and off that piece of metadata hangs these arc buffers. These arc buffers actually contain the data that is being cached. And we can have multiple arc buffers in there, although we try to keep it to the point where we only have one, because what's the point of actually keeping duplicate data in a cache? So if we go into more detail on what the arc header looks like, we see that in there it actually has the size information. It has that same triple that we use to get into the hash table, and then a pointer to the arc buffers. The arc buffers themselves actually store data uncompressed. So the data that's in the cache is always uncompressed when it's associated with an arc buffer. And we've, a while ago, implemented this thing we call single copy arc, which actually allows us to discard these extra copies so that the cache is more efficient. So now we have just one copy of uncompressed data sitting in the arc. So how does this all work when we actually go to read data? What does it look like? Here's a case where we're actually reading data that's currently not cached. So the first thing is we look in the hash table, we don't find it. We then go into the I/O pipeline and request that block. So we're requesting a block from some compressed data that we have here. We're going to read it back. We're going to decompress it in the I/O pipeline and pass uncompressed data into the arc and store it into that arc buffer. We then can pass that back to whoever requested the block. And that's the way that the typical inner workings of the arc would behave. If the data is cached and we actually find it in the hash table, we simply just dereference the hash table, find the header, get the uncompressed data, and pass that back to the consumer. So that's the typical way that you would see arc accesses happen. So now let's go into what compressed arc did and how it changes things. So one of the first things that we did when we started going through the design of compressed arc was we wanted to leverage the fact that decompression is incredibly fast. So those that have ever done any experimentation, for example, with LZ4, will find that LZ4 is actually very fast at decompressing data. Compressing data is a little bit slower, but decompression is actually the fastest thing you can accomplish. In many cases, you're getting about 2 gigasecond per core. So we wanted to leverage that. We wanted to make sure that we wanted to take that fact into account as we're doing our design. We also wanted the blocks in memory to be identical to disk. And the reason for that is if we've already paid for the expense of compressing that data to store it on disk, well, then why, we already have a lot of information about that. We have, for example, the checksum of that block on disk. We can leverage that now in memory. So why not take advantage of all these facts about the block as it appears on disk and keep it the same way in memory? We also didn't want to change a lot about the eviction code. So if you've ever done any kind of research on compressed caches, or even operating systems like Mac OS, for example, that has some compression built into its memory subsystem, a lot of those, what they do is they actually compress memory as it's being paged out. So they spend the CPU cycles when you're ready to actually get rid of it and no longer use it. But compression tends to be a much longer process than decompression. So we didn't want to go down that approach. We wanted to take advantage of the things that are fast versus the things that were slow. So when it came to the eviction code and kicking things out of the arc, we wanted to keep those things simple because that tends to be one of the most complicated pieces of code within the arc. So what happens is you simply just, when you're ready to evict a block, you just simply get rid of it. Whether it's compressed or uncompressed, we have a way to just kick it out of the arc completely. Sorry. I also mentioned that we wanted to utilize the blocks checksum, and we wanted to do this specifically for L2 arc. So do people run L2 arc caches? Some do. People use it compressed. Have you ever done it? Some people. So one of the things that L2 arc does for compressed L2 arc is it recompresses the data before it writes it. But if we have the advantage of actually having the compressed block already in memory, then I can simply just write it. I don't have to compress it again. I already have that compressed data. And I already know it's checksum. And it's checksum instead of being some simplistic checksum that we have to maintain as part of arc metadata. That checksum actually happens to be the strong checksum that is used for whatever block you've written. So if you're a shop that uses SHA-256 and uses a really strong checksum, your memory and the block in memory will now have that exact same characteristic. You'll be using SHA-256 as a checksum algorithm for your block in memory as well as the block you're writing to your L2 arc. Okay, so how did the data structures now change? How does this differ from what I showed you a few slides ago? So here we're looking at the same arc buff header. Again, that same piece of metadata. The thing that we did was we split the size out into two components now. We have the physical size as it is on disk, and the logical size as the client or the reader would want to see it. We still have that same triple that gets us in the hash table. We can still point to a bunch of arc buffers, which have uncompressed data, except now we have this new private data scheme, which points to the compressed data. This data block is special. So this data block actually matches the same block on disk. If the block on disk is compressed, then this block will be compressed. If the block on disk is uncompressed, this block will be uncompressed. And we still have the same advantage of trying to be efficient with the arc. So once the consumers stop actually asking for the data and they've read it, we can simply just get rid of all the uncompressed data, and it leaves us with just this piece of metadata and this compressed block. We also added the ability to share data between the two pieces of, between the arc header's private data and the arc buffer that might be requesting it. This is very useful when you have a pool that has uncompressed data, or maybe, whether it's both compressed and uncompressed. If it's uncompressed, then we already know this block matches the block on disk. So it's going to be uncompressed on disk, then this block will be uncompressed. The thing we know is that all arc buffers that are requested by users always want uncompressed data. So if we know that characteristic about the two, then why not just share that piece of memory instead of actually duplicating it? And that's what we did. So as an additional enhancement to try to minimize how much uncompressed data we keep in memory, we actually can share this data. I talked about the compressed send, and how do we actually achieve that? And this is how. We extended that and said, well, if we can share the data, if we have a compressed block in memory, and we want to send that compressed block, then we would just simply allocate a special type of arc buffer that we're going to pass to the sending thread. We share that data with the arc header, so we don't actually allocate anything new. We just create this little piece of, this little data structure that points to the compressed data, and it can simply pass it back. So this is what it looks like when you put it all together. If we want to read data, we again look in our hash table. We see that we had a cache miss. We go to the I/O pipeline and request the block. The block on disk is actually compressed, but instead of having the I/O pipeline decompress it for us, we simply have it pass back the compressed block as it appears on disk. We then store it in our private data that's associated with the arc header. We decompress it within the arc and pass back the uncompressed data. So this decompression phase that used to happen at the I/O pipeline has now been moved up and now sits inside the arc itself. So in more detail, this is the operation of what it would look like if we actually did an arc read. We start off with the arc header and this piece of empty data. We allocate an arc buffer. We request the data, and we pass our pointer of where to store it. We read the compressed block. We pass the compressed block back into the arc. The arc will now decompress it and store the uncompressed data in the arc buffer. And then once the consumer has read it, we simply discard it. A cache hit looks very similar. We start off with the compressed data. We allocate the ARC buffer where we're going to pass that back to the user. We now decompress the data, store the data in the ARC buffer. Once he's finished reading it, we simply discard it. Writes are a little bit different because one of the things that's happening is when somebody writes the data, they're actually writing this uncompressed data. We don't know what it's going to look like after it's been compressed. So the very first thing that we have to do is we have to get rid of the compressed data we have because somebody's made a change. So that's the first thing we do. We just simply discard the compressed block. This uncompressed data now has the change that somebody has updated. So we pass that data to the I/O pipeline. The I/O pipeline now will do the compression for us as it's always done in the past. And we copy the compressed data now back into the ARC. This all happens before it ever gets to disk. So as part of the I/O process, we've already updated the cache with the compressed block and have that in hand. And then only after that has been completed do we actually write this to stable storage. And again, once the write has finished, we can get rid of the uncompressed data, leaving just the compressed block in the ARC. So this is an example of a real live running system. Are people familiar with arcstat? It's a little Perl utility that's out there, and I think there's a Python version of it too. This was just simply modified to show you a little bit about what the effectiveness is of compressed ARC on a running system. This system actually has 768 gig of RAM. What we see here is that it's only using 64% of the entire ARC in its current running form. So it's using 448 gig of memory. That equates to 1.2 terabytes of uncompressed data. So effectively, we're caching 1.2 terabytes in a 448 gig form factor. We're getting a 275% increase in our caching power. And just to show you that same system, this is, can you guys see that? This screen right here actually shows you that running system today. I've also added this overhead piece. This is that uncompressed memory that stays around momentarily. This is the piece that we're always getting rid of. Every single time we uncompress the data and we pass it back, it's considered, we call it overhead internally, and that's the way it shows up in this category. So we see that we have roughly 800 meg of uncompressed data at one time, and this fluctuates as the system processes. But we're getting almost a 3x improvement in the amount of cache that we have. Yes? This also applies to L2ARC. The same compression ratio that we're getting here would apply as we write the blocks to disk, to the L2ARC device. They're going to the L2ARC compressed. And even better is that when we read them, we know the checksum of that block. It matches the same checksum as the block on disk. Okay. So quickly, I'll move on to the third thing, which is the allocation throttle. So I like audience participation, so feel free to shout things out. When people look at a pool like this, and I'm sure you've been asked this many times, like somebody comes to you and says, hey, I have this pool, it seems to be performing poorly, and you look at it, and this is just using zpool list, and we look at it and we see, oh, okay, well, it's got some free space, that's good. It's not at some ridiculous capacity, so 71%, that's not so bad. So it should behave okay. So we're like, okay, great, free space, fragmentation is low. Good news, good looking pool. But when we actually dig into it and look at each of the individual devices, it may not look so good. So you guys see anything, if somebody presented this, what do you see here that is kind of problematic? Say it a little louder. Free space is not allocated evenly across the devices. Even more interesting, the sizes of the devices aren't the same. So this pool is comprised of 2 different size disks with 2 different sets of capacities. So this is going to behave in a very erratic form, because as we start to do allocations and we start allocating from these devices, it's going to be slow. When it gets down here, it's going to be a little bit faster. So in the end, the performance of this pool, not that good. And in fact, this again is a real system. It really was not very good. So here, I want you guys to kind of observe. Good. These are just kind of static shots of using IOStat. So I just want you to tell me what you observe as I run through these stats. So it'll update kind of in a couple seconds here. Okay. What did you guys see? You want to see it again? What was that? The large disks finish flushing first, correct. We see that, in fact, these devices are not busy at all. And one of the things that we want to do when we're actually writing out bulk data is we want the devices to stay busy all the time. That's why we added more devices. We wanted more bandwidth. So let's keep them busy. So this is what we actually set out to tackle. And this is the same pool that I just showed you where you had the uneven devices. If you were to observe this from the perspective of the fast devices versus the slow devices, over the course of actually writing that data, this is what it would look like. You'd see the fast devices get the same amount of work. They simply complete it very fast and then do no work for the rest of the time. The slow devices get the same amount of work and kind of churn through it at a very reasonable, but maybe much, much slower than what we would like, rate. And at the end, the way that we finish this transaction group and can determine that this thing has synced to disk is not this at the completion of these devices, it's at the completion of the slowest device on the disk. So that's what we wanted to actually go off and solve. And that's where we're introducing the allocation throttle. So the way this works is that now all these writes come into this big allocation queue and they get sorted. There's one advantage here is that we can actually sort them by logical location within the file. So if you're writing and updating a file, then we're going to first allocate block 0, then block 1, then block 2, then block 3, then block 4. We then take a small amount of work and reserve an allocation slot. We ask all the devices to go start working on that small amount of data. So everybody may start off, say, with 100 units of allocation. Everybody gets the same amount of work. We look at the top level queue. We send it out to the actual physical devices. As the physical devices complete, the ones that have completed simply ask for more work. So if this top one happens to be our slow device, then it might take longer to get its second round of work while these other devices are now completing and doing more work as a result. And again, our goal here is keep the devices busy as long as possible. Same system with the new updated changes. So again, I'm going to ask you to kind of tell me what you observe here. Okay. So what did you see? So we're actually seeing that some of the devices that have more free space are actually doing more work. The other thing that we're noting is we're not seeing any devices that are no longer taking zero amount of work. So everybody's staying busy as a result of this. And in the end, we're achieving the transaction sync at a much faster rate. Because now, even though these devices up here may take a little bit longer, they're not being asked to do the same amount of work as everybody else. They're getting a little bit less. They're starting to fill up at a slower rate. But then again, they didn't have as much free space to begin with. So even though they're filling up at a slow rate, that's okay, because we already saw that they weren't the same size, from the onset, and they were relatively full. So in the end, when somebody says, hey, we need you to do less with more, we think OpenZFS is a way you can accomplish this. When you need more flexibility, you can use the advantages of Resumable send and receive. You want some more capabilities and you want to actually be more efficient, compressed arc is a very good way for you to actually achieve that by getting more RAM than is physically installed in the system. And when we want more performance, we can get it out of the allocation throttle and also using compressed send and receive. So, any questions? And by the way, Delphix is hiring in case anybody's interested.
All right, if you have questions, there's a microphone right there. Please line up behind it. We've got a few minutes here. We can take a couple questions. Okay, well,
awesome.
Join me in thanking our
Thank you.